Okay. Is my screen visible?
Yes,
Yep.
I can see it.
Okay. Then let me know when we start.
Yeah, let's just wait 2-3 more minutes for anyone else to join, and then we can start.
Yeah.
I think there was some confusion about the link as well. So
Yeah, I guess not everyone would have registered, I think, maybe.
we do have 19 registrations. So uh, let me update the let me put the update on Mastodon and Twitter and stuff. I think we can start at 7:10 maybe. So that's in 3 minutes.
Cool. Yeah. Maybe anyone who's already here, if they have anything to talk about or questions, we can also do that till then.
So we are going to start in the similar way, but in a more uh, practical way of using Haskell, right? With effects and not involving a lot of theory.
Right, right. So today's talk will only cover like, okay, how you exactly use this. It will not cover anything on the theory side of things, like how is Freer simple implemented or basically these three papers.
Got it.
So this will be the part of the next talk, which I will do, I guess, maybe in 2 weeks.
Nice. I wish there was a way to add everyone or add channel in Telegram. There's not.
All right, we are live on YouTube as well, and I've posted it on Mastodon, the YouTube link, as well as the fact that we're starting and they can join on Jitsi.
Yeah.
All right, I guess we can go ahead and get started. Sanchayan, what do you think?
Yeah, I guess then let's start it. It's almost done. Okay, then I'll start. Uh, yeah. So welcome everyone for today's talk. I'm Sanchan. I'm gonna be speaking about how to use FX system in Haskell. I'm gonna use this freer simple library as for today's code samples. So what today we will not cover is basically how FX systems are implemented. So primarily, for example, if you look at these three papers, they are the basis of how freer simple works. So this we will cover in the next talk, maybe in 2 weeks. For today, we will just see how to actually use them, and what we will also not cover is uh, So there are a few FX system libraries out there. So for example, FreeSimple is one of the oldest ones. The FX systems, as such, the theory part of it has been since around 2001 or such, but the actual practical implementation came around with when Oleg Kiselyov came out with his paper Extensible Effects, and then the next paper, which is Freer Monads More Extensible Effects. Freer Simple is pretty much based on top of those two papers and this additional paper. So FreeSimple was one of the first ones, and then a few others came along. So, for example, this Polysemy, this Fuse Effects. Then the recent ones are Effectful and Clef. All of them, they have very different implementations. So implementation among all five of them is actually different. Effectful and Clef are somewhat similar, but otherwise all of these are different. So we will not go into details of how they are different and what are their implementations are. So I will basically start out directly with more or less from code samples based on FreeSimple. But before we get to that, let's cover the part of why are we even talking about FX systems. So in Haskell, which is basically a pure functional programming language, monads have been the way in how we model FX. So FX are basically anything like IO, or you are talking to a database you want to write or read from the console, or anything which changes the environment of the application program in some way. Now, another way to think about this is anything which you cannot memorize. So, for example, if you have a very simple function like you take a number, the function takes a number and then multiplies it by 2. Now, this function can be memorized. Basically, assuming you had infinite memory, you can store the results in a table and then just do a table lookup. So you can effectively memorize this, and the result is not going to change. If your input is the same, the result is going to be the same. This is not the case with any effectful functions where they are involved. So we use monads to model effects, and in Haskell, everything is about composition and functions. So with monads, as such, they do not really compose. So any two arbitrary monads, if you take M1 and M2, the composition of M1 and M2 need not be a monad. So this is covered in a paper. If you want to dig a bit more deeper, which we'll not do today, there is a paper called Composing Monads from Mark Jones and Luc de Ponche. So it goes into the specifics of how you go about composing monads, in what situation or what specific constructions. But just for a quick know-how, basically two arbitrary monads do not compose. So then if they do not compose, then there's no point in even looking at it, because in Haskell, everything is we need things to compose, otherwise there's no point. Why we even use Haskell then? So a solution to this has been what are known as monad transformers. And what monad transformers do is let's say they provide a construction which allows monads to compose. Now, so this generally so for a long time, the two libraries in Haskell called transformers and MTL, they have been primarily the backbone of, if you wanted to do anything with monads in any library, generally these will come into play. So monad transformers, as they are known. So what does a monad transformer look like? So again, I'm gonna just I don't have any presentation as such. I'm gonna just do code samples and refer some papers. So this is another just like a example paper, monad transformer step by step. So we're just gonna look at one example from that. So what does a monad transformer kind of look like, or basically a monad stack? So you can see basically the final example in this paper is this one. Here we have primarily 4 monads, as you can see. So actually 5. So you have a reader, you have an error, there is a writer, state, and then finally we have the IO. So this is basically your FX stack as such. Each monad in the stack basically gives you access to that effect, so to speak, and the context that comes with that effect. So the most easiest example is the reader. So basically anything you need to read from the environment or provide some kind of an environment as an input to your application, this is generally done through the reader. So this is just one effect in the stack. Same way, if you wanted to handle errors or if you had state, these monads will come into play. So this is what a monad transformer looks like. And basically, if you ever had difficulty in working with monads, the best way to think of it is any what monad is present in the stack, that's the effect or the context that you get access to. This will become a bit more clear if it hasn't been clear to you so far when we look at the effect examples as well. So we'll come to that. So this is how we have been dealing with effects for quite a while. Now there are some downsides to this monad transformers. First of all, the moment you define a particular stack like this is kind of a static. So if you want, so imagine if you just started with the reader T, state, and IO, and then at a later point you wanted to introduce error handling. The moment you change your signature at one place, you will end up changing it throughout your application. So this is not kind of extensible, so to speak, in FX terminology. The other thing is basically your stack pretty much determines how you're gonna handle the effects and in what order. So they are primarily not extensible and they are not very, so to speak, ergonomic to deal with. So generally, one of the recommended ways in Haskell to do this is just the reader T and the IO approach. There is a blog post from Michael Neumann on this, and that goes into the details. But basically, that's one of the sometimes recommended approach when people do not want to deal with the complexities of the stack. Because if you go anything more with 3 or 4 effects, then that becomes a bit unwieldy to deal with. Another thing is, so here we are seeing reader, error, writer, and state. Imagine if you wanted to have 2 readers or 2 states. Because of the way monad transformers or MTL is written, it's not possible to do this with monad transformers. Why this is not possible? So if we look at the monad transformer MTL implementation, so if we look at I'm assuming my screen is visible and you can see the code well enough. If not, please holler. So this is a monad reader. If you are trying something in chat, I don't have access to that, so best is to just speak up in case.
It's fine, you can continue.
Okay. Okay, great. So what I have here is the 2 panes that you see. To the left is the transformers library, and to the right is MTL library. So what transformers give you is basically the monad transformer part. If you see the class example, so this is the definition of monad trans. You can see there is a lift. So basically, to give a quick overview, what they do is if you have a monad M, the result of TM should also be a monad. Basically, it allows you to stack the monads. But the problem is when you have a stack of effects, so if you have a stack like this, so let's say I wanted to run or execute or discharge my state effect. Now, it's basically 3 levels deep. So whenever you are working with this, if we did not have the MTL library, what you would end up doing is you will end up writing what are called lifts yourself, which you see here. And what MTL does is it basically defines a class which is like this, and it basically writes instances so that you don't have to write them yourselves. So for example, what we see here is you have a monad reader and then you have a state. So there's an implementation of this like this for every monad combination. So reader, state, reader, some other monad. And so, but the problem comes is in its definition. So you have, if you notice this, this is what is called as a functional dependency. What that implies is, so when you see a stack like this, if you know the monad M, you know what R is gonna be. So basically it's tied to the type. So if state T is an integer, because of whatever type level machinery, when you in this whole monad stack, when you try to access the state, it's gonna know that it's an integer automatically because of this. But if you had two states, so imagine there is a string and imagine there is an integer. So state t string and there is a state t integer. You will see these in FX also, but there it's just easier. Then your code won't even compile because of this type class functional dependency. GHC can't figure out, okay, when you say whether you want a get or a put, which is basically the interface to state, what do you want? Do you want a string or do you want an int? That is not clear. We'll see how FX systems resolve this. So there are some limitations like this, and basically, if you look at MTL, what is generally known as the n square instances problem, if you try to dig deeper in this. So all those things make it basically not so ergonomic when you want to deal with anything, any more of a complex stack like you see here. So these are some limitations around it. But let's say if you do not follow any of this, that is also fine. We will see, when you see the FX system part, you will see how it becomes ergonomic in compared to MTL. Any questions so far before I move on?
Yeah, so I wanted to ask, I've heard of these limitations in passing many times, but since you worked extensively with Haskell, have you encountered this, especially the using two states in the same stack? Have you encountered this problem in reality, or is it purely theoretical?
So it's not theoretical. So I have not written a whole lot of Haskell. At least the industrial one that I have written on the project I have worked on, that did not use MTL. So I did not come across this problem. But it's a very easy problem. So imagine example. So let's say you had an example like this. We will see. So let's say you have a reader. So let's say this is some HTTP monad, and then tied to this, you could have, let's just say the env is, you have your HTTP URL endpoint somehow with this. This is a theoretical example, so maybe, but somewhat similar to maybe what you would encounter in real world. So you have an HTTP reader monad, and there's an HTTP endpoint env tied to this, and there is, let's say, some config, let's say, just for theoretical purposes. Now, if you had a MTL stack, so basically, when you did an ask, so ask is one of the interfaces of reader, you did an ask, and you are in this stack. The ask will not know whether you want HTTP endpoint or HTTP config. In an MTL, you cannot do this. One way generally people bypass this is you somehow club these two. So either you define some kind of a product type, and then you say like, okay, my HTTP monads env is this product type which has endpoint and config. But then that's not really scalable. Maybe you have a whole bunch of things and you just don't want to shove everything in one particular type. You don't have, let's say, separation of concerns and things like that. So, and you would like that, but MTNL does not give you this. You basically you can carry around only one reader, and then you only one big type tied to that, which FX systems are not plagued by this.
Got it. Yeah.
So, any other questions before we go to the FX examples? Okay, so assuming not, let's move on. So I'm gonna jump now directly to the examples. We will see how we define effects, how we use them with this Free Simple library, and we will also quickly take a look at how it looks like if you were to use polysemi or some others. So the way you start off with is you basically write your effect. The way you write your effect is a GADT style general, what Haskell calls GADT. But even if you're not aware of that, that's fine. That's really not needed. All you need to learn is basically this kind of a syntax construction of how to write your effect. So you define your effect. So this is a name. This is UIO or whatever your actual effect is, and then you define what all things is gonna handle. So I am saying I have a universal IO effect kind of. There is a read and there is a write. Read gives you a string back as a result, and write takes a string and then it discharges that effect. So this is just your effect definition. And then the next part to do is you need to tie this to the effect which is defined by the library. So generally all of these libraries will have an effect monad. Generally it's F, which is EFF, or polysemy has SEM, but they pretty much all are at least they look same on the surface as such. So you can see I have an F monad here. So to tie this to the F monad, you can either use the template Haskell machinery, which looks like this, or if you wanted to handwrite it yourself, that is also fine. So for example, I'll just show, let's say I comment this out and I'll uncomment this. And I think this. Okay, let me, I forgot the types. So let's just I have the REPL started here. I'm just gonna load that, and I'm just gonna write out the type of the UI. Of course, I forgot to put up the type. And so we can play around. We are gonna play around with the REPL a bit. This is not available. Okay. I forget the exact type here. I need to match, but we'll come to this later in a bit. So let's just say, but basically you can either write this by hand. This send that you see, so this is the free or simple library. So what sends does is it basically sends an effect, or basically ties your effect definition to the actual monad. So as you can see, its definition sends an effect, which should be a value defined as part of an effect algebra. Some words to an effectful computation. So you can either do this by hand or basically just use template Haskell, which is this double tick that you see. And the template Haskell extension is also enabled by default in the Cabal project. So that's in effect here. So I can just do make effect, and basically this will tie your effect to your definition of the effect thing. And if we look at the types, so this will expose this two constructions. We can look at it in the REPL type. So let's say write UIO. You can see exactly this type here. And I have not, this is commented out. So basically that is coming into the application code via this make effect call. And then I have the read UIO, which is this type. Maybe I have messed up this. So we use this make effect call, and then you basically have these read UIO and write UIO available to you. Now let's see how we exactly use this. Basically, you are going to use this read UIO and write UIO to actually build your program AST. So what does that look like? So here I have just used I have defined just another function to just say like write program, read program, which is eventually just the same thing. But we are going to see how we're going to use that. So coming back to this definition, one of the reasons why we are looking at this is basically what effect systems allow you to do is they decouple the interpretation of this effect from its actual definition. So how does that work? So basically, here I have read UIO and write UIO defined. I'm going to show you how basically you can interpret it in three different ways. So let's look at that. So we will look at the simplest one, which is like IO. So you can see I have defined an interpret in IO. This interpret M is coming from the free simple library. The types can look a bit scary, but we'll come to that in a little while. So I have this interpret M. I'm handling the two cases, write UIO and read UIO. And then you can see to the right of the arrow basically is your interpretation, or how you are going to actually uh, implement your AST or your interpretation of the AST. So in this particular case, I'm saying that write UIO basically is just gonna give me gonna call put string line, and read UIO is gonna just call get line. So this is in IO. If you wanted to do it in pure way, like I don't want to interpret it in IO monad, I want some other different interpretation. So here we have got another interpretation where there is a state involved, and I'm saying write UIO basically, since there is a state involved, it can do a get, then a put, and then the read UIO is just get. Same way, if I go to a file-based implementation, so I want to interpret my write UIO and read UIO in terms of a file. So write UIO calls a write file, and then read UIO calls a read file. So basically you can see that you had one effect defined, which is read UIO and write UIO, but how you interpret them can be changed in any other way, in any way you want. So a very real world use case is this, where you want, when you have your actual implementation, maybe you are dealing with file IO or you are doing with database reading, writing. But when you want to mock or you want to do testing, you can just switch out your interpretation to something which gives you a pure interpretation without any database being involved. So your interpretation and your effects, they are decoupled, and they can be changed any way you want. Now, how does this exactly work out? So now let's get to the types. So we saw how we defined the effect, which is here. We did a make defect call, which tied our defect definition to the actual F monad, which is what freer simple provides. If you look at other libraries, they also call it F. Polysemi calls it SEM, but on the top level surface, they look the same. And then when you go to your interpretation part, let's look at the type now a bit more closely. So in the case of interpret file IO, okay, we were looking at these ones, right? Okay, let's come to these ones first. So let's look at these three. So we had file-based implementation, we had IO, get line, string line, and we had just a pure state-based implementation. So how does this work? So basically, all the effect libraries pretty much work by tracking the effects in a type level list. So how you define that? So this is just the input to the function file path, which is fine. This is my actual monad. And then this defines my list of effects. So in this case, I have two effects in my list. There is a UIO, which is our definition, and there is the IO monad. And then when you do the interpretation or when you handle the effect, what you do is you might have any list of effects in this list. There may be here, there are two, you may have 5, you may have 6 or whatever. You consume effect, and then the effect that was consumed or that was discharged, then that gets removed. And you can see as in the result type, I only have IO. I don't have UIO, which is this effect. So basically, the interpret in file function body has consumed the UIO effect or has discharged the UIO effect. And then in the end, you are basically remaining with just the IO. Same way in interpret IO, here I discharge my UIO effect through this handler. In the final case, my just IO remains because I have again put string line, get line. Here also, these are just IO. In the pure case, here I started with the type level list of which just has, so this is the constraint. The members or the member constraint. So there is, this basically tells you that you can, So for those who are not aware of Haskell, basically anything to the left of this is basically saying like this is my constraint, some kind of a type constraint which is applicable to this. So here I'm saying for this interpretation, I should have a state effect in the context or in the scope. And then in this case, here you can see UIO, which is the effect that we want. This is, you can think of as a type level concatenation of the various effects that are gonna be your type level list. And then on the right side of this. So let's go a bit more deeper. This that you see, this is what is called as a natural transformation in Haskell. What this does is, we will see here, I have another example here. Same example, but a bit different one for the different effect. So here also we are saying that member is meaning you all defines that at least this should be there. With members, you can specify multiple effects. If you just want to have a constraint where you say like at least this one effect should be there, then this is this member, or if you want more, then you can call members like we have here. So this is a type members, then your type level list of 2 or more effects. Here, since we only needed state, I'm just using member. So using member, you specify like, okay, in this particular implementation or scope, what are the effects that you expect to have? And then, so this is your constraint. And then to the right of this, you can see, again, we have this notation. So here I'm saying file is also going to be in scope, and then the file effect is going to be discharged, and then you have whatever was remaining. So now, what exactly is this? This is called natural transformation in Haskell. It's basically nothing but a polymorphic function, which basically is defined like this. Type FG. So it basically gives you like type constructor to another type constructor, and the type constructor accepts the argument. You can think of it as like going from fx to gx, where whatever argument fx could take, it can take that, and then that will give you something else on the other side. It's primarily just a function and nothing else. We use this because if we do not write this, we can write it this way. This will also work. So let's, if I uncomment this out, this is also a perfectly valid definition. And you can see between these two, this exactly matches what we are seeing here. So since we don't want to write this for all something called as quantification, which I'm not getting into, but if you see this for all x fx to gx, this is exactly similar to this, where we basically, what using this allows is you can hide this a parameter. So you will see this type signature in the figure simple library frequently. If you don't want to use that, if natural transformation confuses you, you can also use this, but then you have to use this for all quantification, which is another thing.
I have a question. Why do you need this for all quantification only when you have a constraint? There are other interpretations that do not need, that explicitly mention A, just the interpret file IO explicitly mention A.
Yeah. So I guess I don't have a good answer to that. So there are two things. The constraint is a bit different one. So constraint is what you have to the left of this type of this thing. That the constraint is this. Wherever you see member as such, that is your constraint.
Yes. So is the for all thing only needed when I use a member constraint, or is it for something else entirely? Like, why is it a for all here and not in interpret file IO?
So I can also do this here if I want. Let's do that. So for all A.
Yeah.
I
It would
think
be the same thing.
So let's see if that works out. And what does GHC tell me? Expecting one more argument. So F has a basically F's type signature kind does not match. I don't have actually a good answer to this, to be honest.
Sorry, this
Okay,
is
okay.
this you require putting a there, right? Why did we take out a?
With
So
for all.
the question is, if I understand correctly, if we compare interpret file and interpret file pure, there is a natural transformation which I'm using in the type here, and basically we are foregoing this for all a here. And but in this signature, we don't have a member constraint, and we are also not saying for all a as such. The a is already part of this type signature. So that's the question as to why is it different.
So in Haskell, the for all is implicit if it's at the top level. So if so here also in interpret file IO, for all is still there. It's just that the Haskell compiler puts it for you. So that's why you can use variables, and the Haskell compiler will just insert appropriate levels of for alls. In the second interpret file pure, what you're not using an a at all here, right? So you're just using a natural transformation, and the arguments to natural transformation have the kind type to type. So this actually does not require an implicit a, because here you are basically passing something which does not require a type to be instantiated at this place. So that's why you don't need a for all a, and actually Haskell does not need to insert it for you. If you convert this to if you add the for all a, then you will need to change it to for all a, and then instead of the natural transformation, you would need to write f something a and a function arrow, and then f something a, right? So you would
Basically
have to
what we have here.
Yeah.
Yeah.
What I'm trying to understand is does it have any semantic meaning, or is this just syntax sugar? Like it doesn't change anything. Like if I write for all a, and if I use natural transformation, it's the same thing as the above. Like, is it just two different ways to
Natural
write it?
transformation is defined in a library, so it's like a type that's been defined in a library. So when you use natural transformation, it's not something that Haskell gives you. It's just like any other code library that you're loading. So that definition is a higher kinded definition that takes a type and returns a type.
And you can, like Anupam said, since the for all is implicit, even if you remove it, that will also work.
Yeah, that's all I was asking.
So, like I have removed it, and this worked. The reason for writing this explicitly was to show the the equivalence of if you use either this definition or when we use this squiggly arrow.
Understood. So all three are the same. Like
Yes,
the
yes.
A is not anything.
Yeah. So if you don't write this, like Anupam said, since in Haskell is implicit, in pure script this would have been explicit, but this is actually there, and to show that they are equivalent, basically, so we write that out. But even if you don't, it's there, because you can see, like, because of the squiggly arrow how it's defined. This is the, if you look at in the natural transformation library, this is the definition of its type. So type the squiggly arrow FG, and this is how it's defined. So it's actually there even though we don't see it.
So one other question. I understood this part. So the constraint is on effects. So you have some effects, and one of them must be state string, and then it could be anything, but it must have a header. Like the first effect must be file, and then you discharge the file effect, right? Something like that is what's happening here.
So we are discharging the file effect in this case, but at the call side, basically when you call this, so we are calling it here. When we run this, we'll come to this. Basically, when you run this, you should have a state involved. Like otherwise, you are gonna get an error.
Oh, yeah, yeah, yeah. Understood. There should be a state string. My question is, it's here. Here, file is the first effect. Is the order of effect important here, like the stack?
No, it's not, because the type level list that we spoke about, that you see like here or here or anywhere else, the actual order is not important. It's basically an unordered list.
So it's a set. Okay, so it's more like a
Yeah,
set.
it's an unordered type level list.
Hmm, hmm. Okay.
So the type constraints basically, so I can, if I remove this will be fine. But the reason for putting this here is, when at the call side, basically when I will call this interpretation from wherever else, I'm saying that state must be present in the scope. Because if you see the actual implementation, I'm calling put. This put is only available if you have a state in context, if you have the state effect on state monad in context. So that's why you see this effect here.
And why are you not discharging the state? Because it's pure. It's like it's not really a side effect thing.
So the state is in the implementation, but it's not in this scope. So basically, this is saying I'm gonna have state, I'm gonna have file
Oh, okay.
in the list, and at the call side, whenever you call it, basically there you need to make sure. Like, so for example, if you just look at this in isolation, you can see I haven't provided any state to it. There is no initial state. Like, so here we are dealing with strings. I haven't provided any kind of a string to which start with. So this is going to come from the call side. So if you look at the call side is here. So you can see I have a run file pure, and that is taking an initial state as argument, which I'm giving to run state. And if you see the run states type, it's gonna take basically your initial state as the first argument, which is coming from here. So this is just basically type level. I'm saying like, if I need to run that, then I should have a state in scope, and the type level constraint is basically making sure that that happens. So this is just for basically, like, you can think of I'm foolproofing my program with types. That's all the constraints they say. Right. So okay. So coming back, so we have specified that the state is going to be in scope, the file is going to be a scope, and then in this case, we are just discharging the we discharge the file effect. You can see this is basically, you can think of it a type level list concatenation, this tick and the colon, and then this is gone, and here you only you don't have the file, you only have the f's. This constraint, like I just repeated a bit before, this basically is a constraint saying that wherever you call this from, you should have a state effect in context in that scope. That's the thing. And if you look at the other ones, so let's go to that. So we were looking at UIO. So yeah, so this was a file interpretation, then we had the IO interpretation, and then we had the pure interpretation. And all of them, they are different. So here we only see the UIO and the IO effects. Here also you have UIO and IO. Here there is no IO involved, only state and UIO, because this is a pure interpretation. And then when you actually run this, so if we go to see how we run this, so I have these three run something defined. So if you just want to run the IO interpretation, then there is a run M defined, and then you just call the interpret IO that is defined here. In this case, run pure, since I mentioned we are using a state, here you can see that there is an interpret pure, which is this, and then you can see run state and then actual run. So the final run that you see is basically just your final effect that you will discharge. Here it's IO, so it's a run M monad. The M is specific, like it's denoting you are going to discharge some monad. And since this is a pure basically run, and then nothing remains in the final line. So if we actually run this, so let's load this, and I already have it in main. So if I run so we had IO and this, so let's actually run this. So let's run first the pure one. So here what I'm doing is, so now, okay, one thing before that. So we had defined the effects, we have defined the interpretation, and now you need to define your actual, like, you can build ASTs on top of this. So what does your AST look like? So here I have a run and read program, which is we defined here. And if we, this is weird. Okay. Not sure what that was about. So you can, if you can see the result, it's basically returning a read state and initial state. So what happened? We are basically just returning a tuple. We are calling run in pure, which is exactly run state, interpret, and then we just take we are going to get a tuple of that state. State, generally, if you have seen the states type, okay, I'm not sure why this is crashing. So states return type is generally something like this. So we are just taking the second of that tuple. And so this is what we get. So how does this come about? So in run pure, this is my initial state I'm passing as an argument. So run state got initial state, and then in interpretation, if we look at how it worked out, so my read program is basically just read UIO. So it will just execute this get and nothing else. So your read P, the first, very first implementation, this first member of the tuple is just going to give me whatever I passed as the initial state. And write P, which is where I'm calling write UIO. If you look at that, so this is my initial state, and then I'm giving it this write program, which is nothing but write UIO. So if we go in run pure, in interpret pure, you can see what read write IO does. So I'm just calling get. This will give me the state that which was passed, which is initial state. And then what I'm returning is I'm putting back a concatenation of whatever came and whatever was I passed to interpret pure, which was this. Does this make sense?
Yeah, I can follow. Just one question: that get add string, is it specifically to overcome the problem where a state there might be two states, one with an integer and one with a string?
Yes. So basically, this is what is known as type application, where you tell to GHC kind of like what you are expecting. Since you might have multiple states or readers, multiple effects with different types, this basically helps to GHC to infer like which one you are referring to. So if I don't give this, REPL is giving me some problems. So this will still work, but if you had two, so we will come to a later example in a bit where we have two different states like here. So there is a array of strings and there is an int. if you don't give the type application in this case, so let me do that. If I remove this, you can see I will have an error because GHC can't infer in this case like which state are you referring to. Are you referring to this string, array of strings, or are you referring to this? In case of MTL, this wouldn't have been even possible. But with FX systems, basically you can use type applications to just say, okay, what is the one you exactly want? So you can have two states or two readers or things like that. As long as they are different types, you can easily access them with type application. So this one, even if I remove it, will work. But just for completion's sake, I've given the type application there.
Understood. I had one more question about interpret file pure. Just one last thing I wanted to clarify
Sure.
about that one. So I noticed that others are using interpret M, but this is using interpret, which means it's not actually running any monadic effects. So is it like mocking the file system? Is that what this interpretation is about? Like,
So this interpret and interpret, the difference is basically this one helps GHC with like type inference. So there is a different type. If you look in the actual library thing, then as such there is a difference, but it's just for helping GHC with type inference when you know that there is a specific monadic effect in the stack.
I meant that
The
pure is actually
pure,
mocking the file effect, right? It's consuming the file
yeah,
effect,
yeah,
but it's not
yeah.
actually firing
So
it off. So
right. So basically,
uh,
I mean, whatever this name be, basically your AST can be interpreted in any way I want, in any way what you want.
hmm. So the
Okay.
effect does
So
not,
for
when you say discharge the effect, it does not need to discharge the effect. It just needs to consume it. Like there's a difference here, right? It's not actually
handle the effect or discharge the effect, you are basically handling the UIO effect,
yeah.
right?
Okay.
How you are handling it is up to you, up to the interpretation. In one case, you might have, so in your application case, let's say this will be, let's say this is database, actual database, okay?
Hmm.
You're doing IO read write from database.
Hmm.
But when you are writing tests, let's say you can provide it from some kind of lookup table. So the interpretation is up to you. The actual interpretation is basically this.
Yeah.
This interpret call, there are one or two variants. They generally help with, they as such they are the same, but there are variants to help with type inference and things like that.
Okay. Got it.
So yeah. So basically we saw three variants where each of them was handled in a different way. Same way, I have defined another, just let's say file effect. Where is it? Yeah, a very simple, just for completion's sake, which just has a read file. And then again, you can see for this case, when I want to return, when I want to actually deal with the file, there is the file effect in scope. And here in this case, the file effect is handled. And this is handled using IO. This text read file is basically has to be in, will be in IO. It's coming from the data text library. But in the pure implementation, which is based off state, there is no actual IO involved. If we run this one, so I'm not sure why is the REPL giving me problems of this one. Okay, let's do another run FPIndia. Let's do this. So you can see it has printed out trying to read file text file dot text, because that's all it actually does. So we have this file program which is basically reading from this text file. I have a text file already in this repo, just a dummy one. So it's taking that and it's interpreting it. So it gets that path, text file dot text. You can see all I'm doing here is I'm not actually reading from the file. I'm just concatenating this. You can bring our string concatenation. I'm just appending that part to this string and returning nothing else. It's pure, and that's what it prints. Trying to read file. That's all. And if you actually wanted to read it, so I have run file IO.
So, I mean, my question is, why would I introduce the file effect if I don't use it? Is there any use case for that? Like, I'm not actually using the file effect, so
This is just an example. Yeah,
okay,
your
this is
actual
an example.
effects.
Okay,
Yeah. This is just an example. Like, okay, I'm defining one more, just a different effect, but you can see like the same thing can be dealt with just read this UIO effect.
understood.
But you can imagine that in an actual application, you might want a separation of different effects if you want it that way. But I mean, totally depends on the application. Here in this example, it's just for completion's sake.
Got it. Yeah.
So we are close to 8 o'clock, and I still need a little more to go. So we'll. Any questions so far on why we are doing this? On what we have seen so far. Okay, assuming no. So basically, the summary is with effect systems, you can decouple the actual interpretation of your effect. This allows nice things, separation of concerns. You can easily do testing or mocking and things like that, and the limitations of MTL go away because you don't have a static monad stack like here. You can just introduce anything at any place depending on what you want. So, and we will see it one step further now. So we saw interpretation of the AST. Now there is something else called, all these libraries, they provide something else called a reinterpret. Like take the effect that you have, which is let's say UIO here, and on top of that, maybe stack on other effects. So let's see examples of that. So I have 3 examples here. Let's see this one. So you can see I have a reinterpret 3 call here. And if you see the signature on this top level, so I just have an input of strings, which is fine. That's just an input. If you see the signature here, there is only, I'm saying there is only UIO in the type level list of effects. But with reinterpret, what I can do is I can inject on a few more effects. So this is my go function, which I'm passing to reinterpret here. Request is this program AST is coming from what we will give as an input. And you can see the type level list here only mention UIO, and which is the input to this as well to go. But now, because of this reinterpret, what I can do is I can inject other effects. So I have error, I have state, and I have a writer, which was not in this top level list. Now, how does this work? So let's just run it quickly. So I'm gonna run in pure. Okay, let me clear this. So run in pure 3. I'm gonna give it a list. I should also have it in history. Okay. So I'm gonna call run in pure 3. I'm gonna give this initial list, and this request that you see which will be basically my AST. So I'm saying write program initial, which is basically write UIO and this string. And then this signature is basically saying whatever is the result of this effectful operation, discard it, and then give it to basically read program is called. So how does that work? So we can see string to 3 as the result. How is this working out? So my write program will basically call this branch. It will write that initial state to this state string, but then I'm not doing anything again with that. So that goes away. Then this read program will call this branch where get will get whatever was passed here. Because if you see this, we are calling run state and inputs. So this inputs is exactly this one, string 2, string 2, string 3. And this is what will come here. Well, it will pattern match this. X will be my string 1 and XS will be my string 2, string 3. And I'm putting string 2, string 3 back in the state, and the result is being given as just string 1. Now, this result, out of this, I'm just pattern again taking something out of that tuple